Okay guys, so now I'm back again. I'm going to show you exactly how we can apply this table in exam questions. So as you can see, we have got question 8 here from a past examination question paper, and we're given a galvanic cell. So since we're given a galvanic cell, automatically we must know from our table we are going to be using this part of the table. Now, the first question is 8.11. What is the energy conversion which takes place in the cell? Okay, so since this is a galvanic cell, automatically we must know that the energy conversion will be from chemical energy to electrical energy. 8.12. It says, write down a balanced equation for the overall cell reaction. So the overall cell reaction is the same as the net equation. So we're going to write the net equation, and to do that, obviously we must know what reaction is taking place here, whether it's oxidation or reduction, and what also reaction is taking place in there. So to do that, the first thing that we have to do is go to the reduction potentials table, and we see which one is the reducing agent and which one is the oxidizing agent. So let's just do that. So as you can see here, this is our silver and this is our copper. Right, you can see I do have copper here, and I also do have this other copper. We're not going to use these ones. And okay, so as we can see here, this simply means that because copper is a higher reducing ability, because the reducing ability increases as we go down according to this arrow here, that means copper is going to reduce silver. In other words, it's going to donate the electrons to silver, and hence the way that we're going to write the half reactions, silver is going to be reduced, or is going to be written as a reduction as it is, and then copper is going to be reversed, is going to be oxidized because it loses the 2 electrons, hence is going to undergo oxidation. Another way that we can look at it is by looking at those values here. The value of silver is more positive than the value of copper. Hence, silver is a better oxidizing agent than copper, or copper is a better reducing agent than silver. Okay, so with this information, we're going to go back to our first board. Okay, so like we said, silver is going to undergo reduction. Take note, here, this arrow is supposed to be a single arrow. You don't put double arrows because that would mean that you're saying silver is undergoing a reversible reaction here, of which that's not the case. It's only undergoing a reduction. And then the same here for copper. Copper is undergoing oxidation. Okay, so now that we know the half reactions that are taking place in both half cells, then we can formulate our net or overall reaction by simply adding the two equations. However, we have to first balance the number of electrons. So to balance the number of electrons, since copper have got 2 electrons or donates 2 electrons, silver must also be able to accept 2 electrons from using 2 silver atoms or ions, sorry. So we multiply throughout by 2. So it's going to be 2 times Ag, 2 times electrons, and then 2 times Ag, and then we add the 2. It's going to be 2 Ag plus 2 electrons to give us 2 Ag solid, and then for copper it's going to be copper to give us copper 2 plus 2 electrons. Then we are going to add this 2. So it's supposed to be an arrow here. So to add the 2, we are going to divide through the arrows. Those species on this side of the arrows are going to be added together, and the ones on the other side of the arrow are going to be added together. But you can see we've got plus 2 electrons here and plus 2 electrons here, so these cancel out, and then we are left with only those other species. And then we're going to write our net equation. Is going to be 2 silver plus 2 silver plus the copper solid give us 2 silver and 2 copper plus in aqueous. And this is our net equation. Sometimes you have to put the phases, and in that case, you're simply going to do this. It's going to be 2Ag plus in aqueous plus copper solid give you 2Ag solid plus copper 2 plus aqueous. This is aqueous, right? Aqueous here. Right, let's move on to the next question. I'm just going to transfer the information that you already figured out. So we know here copper is going to be oxidized, so it's going to be copper 2 plus 2 electrons, and then silver here is going to be reduced Ag plus an electron to give us Ag solid. Right, okay, so they are saying we should write the cell notation. Right, so this is 8.1.3. So to write the cell notation, like we say, the first thing you must know that you start with the anode and then separate them with this salt bridge, and then you have the cathode. And then the phases are going to be separated using a single line. So the way that you're going to write this side, you're going to write the anodic reaction and the cathodic reaction. So that means you have to know which one is the anode and which one is the cathode. And from our table here, you can see in a galvanic cell, the anodic reaction is going to be the oxidation reaction. And as you can see, this is the reduction reaction, and this is the oxidation reaction. And since copper is the oxidation reaction, hence that means copper here is the anode, and then silver here is the cathode. And of course, in terms of the charges in a galvanic cell, the negative charge is allocated to the anode. So this will be negative and this will be positive. So now let's write our cell notation. So our cell notation is going to be like this. We're going to start with the anodic reaction, which is copper. So it's going to be copper, and then this is solid, is separated by a phase line or phase line, and then it changes to copper 2 plus, which is in aqueous, in water, and then they're separated by a salt bridge. And then the other side, the cathodic reaction, which is a reduction, is going to be silver, and then separate silver aqueous, and then separated by a single line, and then the other side is going to be silver solid. So this will be our cell notation. Now let's move on to the next question. Question 8.2. 8.2 is asking us to calculate the initial EMF. So the EMF is the E cell, right? So the E cell, we know the E cell is equal to E cathode minus E anode. Right, let's substitute our values there. So remember our values, we get them from the table. Let me just quickly go to the table to get the values. So from the table of the reduction potentials, we can see for silver, the reduction potential is 0.8, and then for copper, it's positive 0.34. Okay, so for copper, it's 0.34 positive, and for this one, 0.80 volts positive. So let's substitute the values. It's going to be equal to the cathode. The cathode is silver, so it's going to be 0.80, it's positive, minus the other one, 0.34 on the anode, is also positive, 0.34. And then we compute in our calculators, we are going to get, and we get 0.46 volts. Then the last question on this part, it says, in which direction will the electrons flow? Write down only from Ag to Cu or from Cu to Ag. Right, so it's going to be 8.3. So remember, the electrons, they always flow from negative to positive. However, electric current, the convectional flow of current is from positive to negative. But take note, electrons are always going to flow from negative to positive. So they're going to flow in that direction. So they're going to flow from copper to silver. So it's going to be from copper to silver, because like I said, electrons, they flow from negative to positive, but current actually flows from positive to negative. Okay, now let's move on to the next question. So the next question is saying the diagram below represents a galvanic cell operating under standard conditions. You can see the diagram. Okay, so let me just take this opportunity to explain the standard conditions here. Standard conditions for a galvanic cell are 1 mole per dm cube, concentration of the solution, and pressure if they are gases. In this case, there are no gases, so you can't talk about pressure. However, pressure, if it was there, will be 1 atmosphere. And then in terms of the temperature, a temperature of 298 kelvins. Those are the 3 standard conditions that you should know. Now, let's go to the question. Question 8.4. So question 8.4 says the cell is allowed to discharge for a period of time during which the mass of the copper electrode changes by 3.2 grams. So the mass of this decreased by 3.2 grams. Okay, we know that it decreased because copper is undergoing oxidation. In other words, it's actually dissolving, and silver is undergoing reduction. Hence, the mass of the silver there will build up there. Right, okay, so the mass here will be increasing. Okay, so anyway, moving on to the question, they say calculate the expected mass change in the silver electrode. Assume that the change in mass is only as a result of the oxidation reduction as the cell discharges. Okay, so here the only thing that you have to do is a stoichiometric calculation. Since it's stoichiometric calculation, we need an equation that links the two. Hence, we are going to use our equation that we did in the first question where we calculated the net equation. So our net equation was copper plus Ag. Okay, this was 2. Give us copper plus Ag. And since copper is undergoing oxidation, it was from copper 2 plus, and then Ag from Ag plus to Ag solid. Right. Okay, so as we can see here, according to our equation, okay, this is 2, sorry. So as we can see here from the balanced equation, 1 mole of copper is going to actually produce 2 moles of silver. So what we are going to do is we are going to calculate the number of moles of copper, and then we use those number of moles to calculate the number of moles of silver that are produced, and then we convert those number of moles of silver that are produced into a mass. So in that case, that's what we're going to do. So it's going to be number of moles is equal to the mass of the object. Okay, so the number of moles is going to be equal to the mass over molar mass. So the number of moles will be equal to the mass, which is 3.2, over the molar mass, which is the atomic mass, in this case 3.55. Hence our number of moles are going to be equal to 0.053. Okay, great. So we're going to use this number of moles of copper to actually calculate the number of moles of silver. Hence it's going to be equal to 0.05035 is to x. Do the cross multiplication. So the number of moles silver is going to be equal to 2 times 0.05035. This will give us 0.10071 moles. Right, now that we have the number of moles, we can actually calculate the mass. So using the same equation, the number of moles is, let me use another color here. The number of moles is 0.10071 is equal to the mass over the molar mass of silver. Okay, the atomic mass of silver is 108. Hence the mass is going to be equal to 10.88 grams. Right there is our final answer. Okay, now let's move on to the last question. Right, so in this last question, they're saying that the silver half cell, which is this one, is now replaced with a standard hydrogen half cell. So a standard hydrogen half cell like this right there, and then where you have hydrogen coming in, and this will be platinum, and this will be a salt of hydrogen with protons. Right, so this is the standard half cell form for hydrogen. So we have replaced it with this. And then for your information, the half cell potential is 0.00 volts. And remember, for this one is 0.34 volts. Right, okay, so the first question is asking, right, is the copper electrode the positive or the negative electrode? Refer to the relative strength of the reducing agents to explain the answer. So again, we can actually go to the table of reduction potentials. So remember, now we are comparing, the copper half cell with the hydrogen half cell. So there are two ways here. Like I said previously, what you can see is as we go down the table, the reducing ability increases. So here, copper is a stronger reducing agent, and then this one is weak. In other words, a strong oxidizing agent. Okay, another thing that you can also look at, like we said, are the values of the E cell. This is more positive than the hydrogen half cell. So in other words, it's a strong oxidizing agent. It cannot reduce the hydrogen. So like I said, copper is a weak reducing agent and hydrogen is a stronger reducing agent right there. You can also see from the values, this is less positive or more negative than this. So anyway, basically here obviously you have to understand the fact that since hydrogen is a stronger reducing agent, then that means it's going to reduce copper, and then itself is going to undergo oxidation. So in other words, here there is going to be oxidation, and here is going to be reduction. And from our table here, in a galvanic cell, the anode undergoes oxidation. So that means this is the anode, and then this will be the cathode. And then on the other hand, in a galvanic cell, the anode is negative. So this one will be negative, and this will be positive. So to answer the question, this is 8.51. So the copper electrode is going to be positive, and then of course the hydrogen electrode is going to be negative. So to explain this, what you're simply going to do is you're going to say that hydrogen is a stronger reducing agent than copper. Right, and then the last question is 8.5.2. Write down the EMF of this cell. So the EMF of this cell is going to be plus 0.34 volts, because as you can see here, the E cell of the hydrogen is 0, hence whether addition or subtraction is still going to be the same, 0.34. Great, guys. This is the end of the question. If you enjoyed this, please like and subscribe.